Alright, heck yeah. So we got material mechanics and we have a spring problem, and I got messed up on this one. And it's because in material mechanics and all of physics that I've just used that the force of a spring is just the spring constant times the change in the distance of the spring. And I've kind of always just used this as a positive number, and then just did my due diligence. So if here's a spring at normal length, and I pull the spring this way, well, guess what? Guess what that spring's going to want to do? It's going to want to go this direction, and it's going to pull. So if I actually connect it to something, it's going to pull on that thing that way. You know what I mean? Compared to, let's say I have this spring, and then I really bunch it up to like half its length. Well, guess what? It's going to want to push something that way. So if we have a spring like this, and then we connect some sort of mass to it, it's going to take this mass and push on it this way. So, and I think I just do this intuitively. But then I wrote down, in some of the problems I've been doing, I wrote down that the force of a spring was just kx, and that is not true. The force of a spring is negative kx. But I just took this equation, probably from what I learned in Hooke's law, and just said, hey, the force of a spring is k change in x, or force of spring is k change in length. You know what I mean? So we have a spring that has an initial length, and I say, hey, the force in the spring is its change in length. But then I think I was just using this as, hey, the absolute value of the change in length. So you can do that. The force in the spring is equal to the spring constant, absolute value of the change in length. You know what I mean? You get the S, no matter if the S, so if the spring is all bunched up this way, here's your S. You know what I mean? In this case, your S is negative. In this case, your S is positive. But if you take the absolute value of it, and then you just do your due diligence and say, hey, the spring's in compression, then you'll just work it out. So what we're going to do is like, hey, well, let's just take this problem and use that just matter-of-fact approach that, hey, I'm just going to turn Hooke's law into the force of a spring is just k change in length. And I'm going to know that I'm still using this as k, absolute value of change in length. I'm going to figure out the change in length of the spring, and then I'm going to put the arrows the way it obviously makes sense. Okay, so let's say we have this spring fixed. It's not really fixed, it's just floating. But let's say it is fixed. It's like welded to this part, this part. But right here it's able to, it's a release valve for like an air tank. So this spring is able to squish up, and then air is going to be able to get through this orifice and escape. Okay, and let's say H was just the initial spring length. So if I just throw a spring in there, one of the definitions of a spring is a spring will have a natural length, and if we use this equation, the force on the spring is equal to k change in length. Well, if we say we haven't changed the length, that's k, and then what the hell is change in length? Change in length would be like length final minus length initial. So length final is L naught, and then length initial was L naught. So our change in length would be 0. So guess what? The force on a spring that is at resting length, it's not exerting a force this way. It's not pushing anything that way. It's not trying to pull anything back in on itself. So but then this also is a fundamental where it's like, hey, if you have a spring at natural length, and just like and I just push on it just a little bit. The first little push is like, hey, I can get this spring to, delta. I can get this spring to change length, just a tiny change in length. By almost putting no force on it. So a natural length spring, it really takes like no force to get it to move, no distance. And I know that it's nonsensical, but it is because of this. Hey, it's not going to take any force at all to move it it's going to take a very fractional amount of force to move it a very fractional amount of distance. So if this pressure relief valve actually is going to work, we have to like bunch up the spring. We have to take it from its natural length, which might be here, and then bunch it up into this length. You know what I mean? So then, to actually get this spring to move, well, we do have to put a force on it. And the force is equal to, in Hooke's law, is K times S. So if this was S, well, that's the... If I want to move this spring any farther, I have to match the force that it's actually pushing. So this force of the spring is Ks, and I would have to put a force equal to Ks to just hold it, to just rest it in place, and just slightly more, and then air molecules can get through. So that's the bread and butter of this problem, and it's super simple. I like to, sometimes I like to do free body diagrams as just like a point, like, hey, this is our point. We're going to have this pressure. I even had to look this up. Like, what's the definition? Like, what's the definition of pressure when it comes to force? Well, the units are the equation. Pressure is in pounds per inch squared. So guess what? This is pressure. It's a force divided by an area. So hell yeah, pressure in pounds per, PSI is force divided by area. So the force due to pressure, just rearrange the equation, is pressure times area. That's it. So hell yeah. So we have a force due to pressure, and then right here we have a force due to the spring. Force due to pressure is the pressure max inside the tank times the area, and that's the second the pressure force is going to equal the spring force. Then hell, like I said, go back to that. Hey, how much more force is going to take the change in length? Almost not any at all. So that's when air molecules are going to start moving through there. Force of the spring is K, and I'm just going to do change in length. But this is where I got messed up, because if I say, hey, the change in length of the spring is equal to the final, length final minus length initial. Well, length final is this H, and length initial is L naught. And L naught is a bigger number than H. So this change in length will give me a negative number. So that's where I got messed up, because just my drawing, my use of this equation is wrong. My use of this equation is wrong, because force of a spring is negative Kx. It's a negative K change in length. You know what I mean? Because then if I do have a negative change in length, well, then the force is going to be... So let's take one look at this, and let's make a longer video. Let's throw some more time on the clock. Okay, hell yeah. So let's go back to just our original picture of what a spring would look like in a textbook. You have it fixed to some side. Here's its natural length, L naught, and then we're going to attach it to a block. And right here we're going to say... we're going to say, and then get rid of the block. Just pretend the block's there. But we need this L naught. And we need to say, hey, this point right here is our starting value for X. And we're going to say this is the positive direction. And then we're going to say, hey, if I have a force in this positive direction, how would I get a force in the positive, especially with just a spring? A force in the positive direction means that this mass is moving that way, because F equals ma. So if I have a force in the positive direction, acceleration is in the positive direction. But the only way to get a force in the positive direction is to bunch this spring up and now put the block here. So now that this block is here, heck yeah, I am going to visualize motion or acceleration in the positive direction. Hell yeah. That means that spring in that orientation is causing a force, a spring force in the positive direction. And guess what? Guess what though? Our S, or our change in length, or our change in X, is going to be negative. So in physics books, force of a spring will be negative Kx. So right here, our x is negative, because here's like positive 1, positive 2, positive 3, x. Maybe these are inches, you know what I mean? But now we have a negative 1, negative 2. So our x is like negative 2 inches. And then our spring force, and then K, because if this is in units of inches, and this is in units of like pounds, well now you know the units of K. K is going to be in units of pounds, pounds on top, inches on the bottom. Let's write it over here. Pounds on top, inches on the bottom. This fundamentally, because the units are the equation, if x is in inches, inches cancels with the spring constant of pounds per inch, and then you're just left with pounds. Cool. So now let's say this spring generates 10 pounds just by moving it 2 inches. Okay, so we have 10 pounds, and we have negative k times negative 2 inches. So what's our k value? Well, these all become positive. 2 goes downstairs, and our spring constant is 5 pounds per inch. Does that make sense? We move our spring 1 inch. The spring now has a force of 5 pounds in it. Okay, now let's take this same model and then move the natural length right here, and then move the spring just longer to out here. You know what I mean? Now we moved it 2 inches in the positive x direction. So this is x positive, and we moved it 2 inches. Cool. Force of a spring is negative kx. Now we have negative k times positive 2. And then our spring constant was 5, so we have negative 5 times 2. And the force of this spring is negative 10 pounds. Now what the hell does that mean? Well, if we have a mass on it, the force is going to be in the negative direction, because we already said this is positive. So now we have a force back. So and if you take any spring, you know what I mean, especially if it's fixed, and here's its natural length, this is kind of your equilibrium, right where the initial length of the spring is. So if you pull it this way, a negative force will bring it back to equilibrium, and then a positive. No, that's not true at all. Holy toilet! That's the issue with springs. It's like just getting fundamentally just like one thing at a time. You know what I mean? So if wherever this mass is, you're like, hey, what's the x? And the x is in the positive direction. Cool. The force of a spring says negative kx. That means that the force is going to be negative. You know what I mean? It's going back to its original length. Compress it. You know what I mean? Now our x is in the negative direction. Negative number goes in here, multiplied by this negative. Then 2 negatives cancel, and we get a positive force. Sure, because the positive force is in the positive direction. Cool. Now, I mean, you can ruin the whole game. Well, let's break out another sheet of paper, throw more time on the clock. All right, hell yeah. And I think you can ruin the whole game by being like, you know, just change it up. Like, well, let's see. Let's say we're saying this is now the positive value of x. So this is x, and this is going to be positive x. Well, now, force of a spring, it probably won't make sense. Negative kx. So now we're going to have it bunched up, and then this spring is going to have a force in the. Well, maybe it will work out. So now the force of the spring will be in the negative x direction. So we're hoping to get a negative force. So right here, we're shooting for this spring force to be negative. We're going to see if it is. So we got negative k. Well, what's our x value? So if we started here, this is x equals 0. This is going to be a positive number. So we're going to say, hey, this is a positive number. And cool, we get the force of a spring. We wanted a negative number, and it is. So we get a negative number for the force of a spring. So this is cool. This is a fundamental where it's just like, hey, the force of this spring is a fundamental component. Like this equation works no matter what direction you put x. So any problem that you have dealing with the spring, if you want to do it from a technical perspective, I would, hey, draw a line in the direction of a spring, because you can't have your x and y be this way. You know what I mean? You can't have x and y be that way or something like that. But anyway, so and then you just have to pick. So what I would do is say, hey, I think the original length of this spring was like here. So I'm just going to say that is x equals 0. And then I'm going to say, hey, this is the positive x. So this is the positive x direction. And then when you compress a spring, you're going in the negative x direction. But we just proved that it doesn't matter. You know what I mean? If you call this the positive direction, it still works out. So let's do that, because I don't even believe that. You know what I mean? For whatever reason, my mind is like, nah, it doesn't seem like, it seems like you have to choose the x direction 100%. But first, I should show you how I got the problem wrong, and that'll make more sense. So I just did the classic, being like, okay, the spring force has to equal the pressure force, and then I said the force of a spring, I used the wrong equation. I said that's going to be K change in length. Cool. And then I said change in length was length final minus length initial, where L naught's going to be bigger, H is, you know what I mean? And then I already in my free body diagram showed this force going down. So I said spring force this way, and then I said force of pressure going that way. So my sum of the moments in the y direction, those have to be 0. So I have basically get force of the spring is going to equal the pressure force. Once those two are equal, hell yeah, you're going to start to get molecules. Like basically once this gets just slightly bigger than this spring force, you're going to get molecules to come through here, and pressure is going to be released. Okay, so it was really simple for me to do that, but I got the wrong answer, so we're going to go over here. Force of spring is force of pressure. Force of spring is K. H minus L naught is equal to force of the pressure. Again, force of pressure, what the hell is that? Well, that's in PSI. Pressure is the equation where you got pounds divided by inches squared. That's force over area. So hell yeah, force over area. No, I'm sorry. Pressure. Pressure is like, strength in materials. That's sigma. You know what I mean? That is PSI. So this would be like sigma. I mean, this is pressure. You know what I mean? Turn sigma this way, you got pressure. So pressure is force over area. Apologize about that. That might be a good way to remember. You have rho, which is pressure for fluids, but then you have sigma, which is pressure in solids. You know what I mean? So, hey, those two Greek symbols kind of look the same. All right. So, pressure, the force due to pressure. The force due to pressure is the pressure times area. So, there you go. Booyah. Let's throw that in. So, we have P max times area. That's going to be P max. The area of a small circle is just pi over 4 diameter squared. And then what we're trying to do is get an equation for H. You know what I mean? That's what the problem says. So you factor this through, so we get KH minus KL naught. And this doesn't have an H in it, so we can bring it to the other side. So we're going to have KH is equal to P max pi over 4 D2 plus KL naught. And then you're going to divide by K. So H is all this divided by K, and then just L naught. And now I get something like this is wrong because I used the wrong equation. I used the spring force equation with a positive instead of a negative. And I could have caught my error, but I didn't. But I mean, right here is where I should be able to catch my error, because I say this height is the initial length of the spring plus something else. Yeah, right. No. This H is the initial length down here minus something else. So H should be equal to the initial length minus some function of P max. You know what I mean? So that is ultimately what we were trying to get. All right, let's throw some more time on the clock and see how we can change. Okay, here we go. Okay, hell yeah. So we're back. And we want to use this Hooke's law. You know, I think it's simple just to be like, hey, force is equal to K times the chain KS. You know what I mean? So that's how they have it written here. But I'm gonna invent my own equation that says, hey, force is equal to K absolute value of the change in length. So whatever the change in length is, it's the absolute value of it, and then you use observation to show the direction of that spring. So that's the way I want to do it. Let's use the actual you know, the formula for a spring. Let's just get used to it. So we have negative K change in length. This will work 100%. So let's do it. Force of a spring, free body diagram. Force of pressure has to equal force of spring. Cool. And even just right here, well, I don't know. Like, could I write this? I like maybe for a separate video. Could I write this like this and still get the same equation? I think so. Is because if I wrote it like this, my sum of the forces in the y direction are just going to get me that the force of pressure has to equal negative force of the spring, or force of the spring has to equal negative force of the pressure. So I definitely know the pressure is in this direction. So that means, you know, by summing the moments in the y direction, the force of the spring has to be downward. So let's use that as a proof that we have the force of the spring downwards, force of pressure up, and then some of the forces in the y direction just shows that these are going to be equal. This had an initial length of L naught, which was down to here. We have a change in length, which is L final. That's going to be H minus L naught. This is going to give a negative value. Cool. So force of the spring is negative K change in length is equal to force of pressure. That's P max times the area. And now let's throw in change in length. So we got negative K. That's going to be length final, which is this H, minus length initial L naught equals to P max A. So now we have, we can factor through this negative. We can go negative positive. So that negative goes away. Now we got negative KH plus KL naught is equal to P max area. And then we can factor out a K. So we can divide everything by the spring constant. And then we get negative H. Holy hell. Yeah, I don't know why I'm losing my mind. But yeah, negative H plus L naught is equal to P max area divided by the spring constant. Cool. Now we can get H by itself. So, hey, let's just maybe bring it over here. Then it's positive H. But then we got to bring this to the other side. So we'll get H is equal to L naught minus P max area over K, which is our final equation. H is equal to L naught minus pi over 4 P max diameter squared divided by K. So this pi over 4 d squared is the area. That's the area. P max is P max. Spring constant is K. So now you have an equation that makes sense. You have this H is equal to the length of the spring, the initial length, minus some sort of, you know, some sort of function that relates P max and the spring constant and the diameter. So there you go. We have a function of H that you know, is a function of L naught, P max, and diameter, and the spring constant K. Hell yeah. But you know what I mean? So that was the one trip up that I got. So now I might as well just always use this equation. You know what I mean? So let's try it one more time and see if I could use this equation and see how and why I could use it. I don't even know if I can. I don't even know if it makes sense. All right, here we go. Okay, hell yeah. So I want to use the equation for a spring just to be like, hey, at the end of the day, I just want to keep it simple. I want to know the force of a spring is some sort of spring constant times the change in length. Let's see if this makes any sense at all. So I have L naught. So then I can just always, so if this is the absolute value, just always take the bigger one. So I know that change in length for ours is going to be, just in general, L naught minus H. That is going to be the change in length that we see. So that's the, and I just know that this is going to be a positive value. If this is a positive value, then I know the spring force is going to be a positive value. But I do know that this spring, by observation, is all crunched up. So I do know it's putting a force in this direction. So there you go. So the force of the spring is in that direction. I do know that this pressure is putting a force of pressure in this direction. By observation, I know that these have to be equal. Yeah, so here's this is probably even more too confusing to me, because this is not change in length. Physics, you know, even your physics books would be like, hey, let's say you have x initial is equal to 1, and then x final is equal to 2. You know what I mean? Your change in x is always x final minus x initial. It's never, change in x is never x initial minus x final. You know what I mean? If you do this, you would have to, you know, but what we're showing is that change in length, the absolute value of change in length is both x final minus x initial, absolute value of that, and x initial minus x final, absolute value of that. So just with one equation, you can kind of do either way, but then you're getting something that's, you have to interpret this value. So yes, you're getting a positive answer no matter what, but then it's up to you to interpret that value. So because this, yeah, sure, we got change in length, but this equation says, hey, we want to get the function, we want to get a function as a, we want to get an equation as a function of h. And so here it's kind of written wrong, because this is length initial and this is length final. Well, length initial minus length final is not change in length. You know, from a definition standpoint, it would be this one, which is not right. You know what I mean? So that's where you would have to do the absolute value. So yeah, so it is probably nonsensical to do that. So let's try it out though. But I think just any problem just to start is just like, hey, what's the change in length? Well, it's going to be L naught minus H. You know what I mean? That's what I see. If I want to get the positive value, because we live in like a geometric world where, like, let's say there is no negative. You know, it's like, hey, like how many apples did you buy today? Well, I bought -2 apples. You know what I mean? In a way, negative numbers are a little bit nonsensical. But if I look here, due to geometry, hey, if someone's like, what's the change in length of this spring? You know, measure it. I'm going to be like, well, I measured it to be 2.5 inches. That's the change in length. You know what I mean? We don't live in the world where it's like, hey, I measured -2.5 inches. You know what I mean? So that I am going to try to use this, and we'll try to use it once and do it all the way through. A little more time on the clock. All right, so yeah, and this is the last page. So let's try it out. So force of the spring has to equal force of the pressure. My free body diagram says, what the hell does it say? I'm going to say, yeah, change in length was a positive, but it squished it in compression, so I know my force. Same thing with the force diagram. Force of the spring is going to have to equal force of the pressure. F of S is equal to FP. Okay, but now when I write the equation, well, what the hell am I going to write? I still have to mind this absolute value. So I'm going to say, hey, K, absolute value of the change in length is equal to P max area. Cool. See, but yeah, now if I want to get a function, I want to get a function of h, I have to be very mindful of this change in length. You know what I mean? Because I already defined it as a positive value, which was length initial minus length final. And that's not change in length. Change in length is length final minus length initial. So, I mean, I could still do this. I could put the absolute value of length initial minus h, which I clearly want to use it this way mentally for some reason. But maybe I'm making this video just because I caught my error and be like, no, this isn't the force of a spring. Force of a spring is negative K change in length. You know what I mean? Where if you get a negative change in length, great, you get a positive force. But if you get a positive change in length, you get a negative force. But I just thought that even just right there is too advanced, where it's just like, it just looked like, hey, Hooke's law is just like, hey, it's a positive, hey. But obviously, yeah, even this might be, because, yeah, even this is saying, hey, the force is going to be that direction. But now you have a force in the, maybe the negative direction. I don't know. We'll see what we get. So we get down to here, P max is equal to area. Yeah, it's the absolute value. I can't do it. You know what I mean? So we're going to have to take a pause on this. And because, yeah, fundamentally I got the wrong answer. Because this one said find an equation with respect to h, and this is where I got fouled up. But there's plenty of problems where even just this one, you know what I mean? Using this equation it's going to, like, hey, if we used force is negative kx, then we're going to say, hey, this is the direction of x. This is going to be positive. We're going to say x is a positive number. Our force then is a positive. So our force would be negative. Yes, and we get a force in the negative direction, because we pulled the spring out. But using this, it says, hey, force is just measure this distance and then multiply it by the spring constant. And just visually, the force is that direction. You know what I mean? You don't, you know what I mean? And that should just make visual sense. It's like, hey, I had a spring that looked like this, but now the spring is way out here. It's going to induce a force this direction. It's going to pull an object this direction. And then this is my S, or my change in length. So there you go. So if I did this problem, I could just do, force is equal to K change in length, which I have been doing with kind of the absolute value. So I found the change in length and then multiplied it by the spring constant, identified a force, and I just know visually it's in this direction. But again, if we wanted to do this problem 100%, we got to go force of the spring is negative K x, negative ks, negative k change in length, which is for the x value, if this is L naught, you're always going to put this as your x equals 0. So cool, now we're going to get and then we're going to, let's do this is positive. Yeah, so let's do this, let's do that one 100% and end the video, because that will end on a very conclusive note. More time on the clock. Alright, hell yeah. So we are going to get a spring with a natural length. Sorry, gotta get more light. Okay, this will at least answer my question. So this is the original length of this spring, and we are going to change its length. We're going to make it longer. Cool. And we're going to do this problem twice. So it's going to be the same length there. You know what I mean? So here's L naught. Here is the, this value is the change in length for the spring. Let's define terms. Length final is equal to L naught plus change in length of the spring. Therefore, even just right here, you can solve for change in length of the spring. That's going to equal length final minus length initial, which, you know, classically and only should be used for change in anything. Always final minus initial. I mean, that's the fundamentals of differential or calculus. Okay, so but now we're going to say, hey, this is x equals 0. For this one, we're going to say, hey, cool, this is going to be the positive x direction. But for this one, x equals 0, we're going to say, hey, this is the positive direction. Both are going to yield the same thing. We're going to throw the block in here on both of them. And if we do a free body diagram, on this one, in an initial, and there's a block, there is no forces, no force. But in this one, hell yeah. This thing is all going to want to pull this block that way. Force of the spring. Cool. This one, same thing. Same thing. Oh, sorry. Force of the spring is going to pull it that way. But we're going to use, and then we're going to use force of the spring negative kx. And in both these, so that's what I kind of just wanted to prove. It's like, hey, I can choose. Always choose your x naught. You have to choose your x naught at the natural resting place of the spring. So if you just have a spring that's just resting on a table, that is its L naught. Cool. All right, for this first one, we're going to go force of the spring is, and even right here, even though I drew these in, we do not know. If for this first one, if I get a positive force of the spring, that means the force is going to be in this direction. This is a positive force. If I get a negative for this equation on this drawing, this is the force of the spring in the negative direction because we're in the negative x direction. So this is positive x. So we have our x is positive. This is 0, so this is negative. This is positive x. This is 0, so this is the negative x direction. Cool. All right, let's do it. So for this first one, force of the spring is negative k, and then our this is positive x, so we're going to get a positive x. Cool. So the force of this spring will be negative kx, and then we get a negative answer. You know what I mean? All right, so now let's do this one. And a negative, like we said, this was the negative value for this one. So, okay, so in this one, let's do that same thing. If this is x equals 0, and we said this is positive x, a positive force will be in that direction. Force spring positive will be that way. If this is the negative direction, a negative force will be something trying to move the block in the negative direction. So that would be a force negative. See, and they're exact opposites of what we drew. But our equation still works. So we're going to go force of the spring is negative kx. Force of the spring is negative k. Our x value in this one is in the negative x direction. So we got negative x. So the force of the spring is going to be kx. And that's going to be a positive spring force. And right here is what that's going to look like. So booyah. So in both these representations, same equation. So now I can just use this and I don't have to use anything else. You know, I might use this just force is equal to ks, but it was just so wild that I was using this the entire time. I even told it to my brother and he's like, no, force is negative ks. And I was like, nah, you don't need to do that. But then I got a problem that says, hey, find a formula, as a function of h. And h was buried into this change in length. And I did it reversed. I did it in the way you're not supposed to do change. I did change in length initial minus change in length final. And that got me messed up. And then I even tried to backpedal even today and be like, well, can I use change in length as an absolute value? And for some problems, yes. And that's basically what this Hooke's law is. As long as you're finding the change in length. Even like right here, it's like, hey, like we said, someone measured this as 2.5 inches, but you know the spring is compressed. So you know the spring is putting a force in that direction with a magnitude. The force of the spring, absolute value, the magnitude of the force of the spring is K times the change in length. Oh, so there you go. So that's full circle. So this equation, force of a spring, the magnitude of it is equal to K times the magnitude of the change, or the absolute value of the change in length. So the magnitude of the force is equal to the spring constant times the absolute value of the change in length. You can use this equation, which is very similar to this. I think this is like, hey, the magnitude of the force, because it's not a vector force. You know what I mean? Else you'd probably want to use this for springs. The vector force of the spring is equal to negative kx. And x is a vector in a positive or negative direction. It's not a three-dimensional vector, but it's a two-dimensional vector. You know what I mean? You can't just say x is 2 because it might be x is equal to negative 2. You know what I mean? Cool. Alright. So that does it, yeah. So the magnitude of a force could be equal to K, the absolute value of S. Or the magnitude of the force is equal to K times the change in length, the absolute value of the change in length. So hell yeah. So I still think I will use this down the road, but I'll be hella cautious because I got into a trap of not using this as my spring force. You know what I mean? Traditionally, let's write it one more time. The force of a friggin' spring is negative kx. Negative. Holy hell. Alright, well thanks for joining for me on this one. I really wanted to do exactly what I did in this video. Do a little learning as I go, come to some conclusions, not have a conclusion, you know, right at the get-go. And we learned a lot. And I think, all in all, it was a pretty decent video. And hell yeah. So I am going to use this. But if I can and make more videos on it, I am going to use this too. The magnitude of this of the force of a spring is is K times the absolute value of the change in length. Alright, hell yeah. Thanks for joining me, and that's a video.